Okay, good morning, everyone. We'll start sharing the screen. All right. So this is the last slide of last class. So we had introduced the Kramer-Lundberg model, and we had denoted by ST this object, summation I going from 1 to NT xi, and so on, where N is a time homogeneous Poisson process with arrival rate lambda, and xi's are IID random variables, actually strictly positive. And this expression is to be interpreted as 0 if nt omega is 0, and otherwise it is x1 up to xk if nt is equal to k. So this is called this is the total claim amount up to time t in that insurance model. So this is also called claim amount process. And this is a compound Poisson process as we had seen last time. Okay, we will continue with this model for quite some time. So there is, now we will call what is a discounted total claim amount process. So you know that if you invest 1 rupee today, and let us say the rate is compounded continuously, and the rate of interest is R. So after time 10, it will be e to the power R times 10, the whole thing multiplied by 1. And similarly, if you want about 1 rupee to available after 10 days, the amount you should have now on hand is e to the power minus R10 into 1. So in that context, it is called a discount rate. So that is why this is called discounted total claim. So let R be the positive number denoting the interest rate. It's also called the discount rate if, in the context of, depending on the context. So now define for any positive t, S0t. So it is related to your ST. ST, you note it is this. This S sub 0t is I going from 1 to NT e to the power minus R times WI, where WI is the time at which the Rth or ith claim comes, times Xi. So this is the amount. In other words, if let's say we are also assuming that any claim which comes is instantaneously settled. So, for example, let us say up to before time t, the ith claim comes. The ith claim comes at time Wi. So Wi will be less than t. And let us say you want to pay Xi at that time, that is a claim amount. So at time 0, you should have this much amount, e to the power minus R times Wi, the whole thing multiplied by Xi. Okay. So as usual, this is equal to 0 if nt equal to 0. And if nt equal to k, this is I going from 1 to k, e to the power minus R times Wi, the whole thing multiplied by Xi. Please note it down. So what this means is this S0T is the amount that the company should have at time 0 so that it can meet all its obligations at time t or during the interval 0 to t. So this will be the sum total of the obligations that the company would face during 0 to t. Of course, this is a random element. Please note it down. All right. So this S sub 0 is called the discounted total claim amount process. So this is the present value, that is the value at time 0 of the cumulative claim amount over the time horizon 0 to t. Of course, as I had mentioned earlier, the claim payments is settled instantaneously. There is no delay. If there is a delay, then of course that would involve different aspect of modeling, which will mean slightly more complications. Yeah, note it, please. All right. So this is just to illustrate the thing. Let us say omega is fixed. So if omega and capital omega is fixed, then Wi omega is the claim arrival time of the ith claim, and the Xi omega is the corresponding claim payment that has to be made. The claim size of the ith claim corresponding to the ith claim. So since omega is, let us say, fixed, that is, it is assumed to be known, then let us say nt omega is k. Of course, k will depend on omega. Then S0T omega is this. So this is the amount the company should have at time 0 to meet all its liabilities or obligations during the time horizon 0 to t. Of course, if this omega is known, there is nothing random. So if, since this is not known, that is, this is all these objects are considered to be random variables, and in principle they are random variables, the best we can hope for is try to compute the average amount, that is the expected amount of S0T. With all the assumptions we know. Remember that these Xi's, the claim sizes and the claim arrival times are the claim sizes are assumed to be independent of the claim number process NT. That is, Xi would be independent of Wi. Yeah, you may note it down. Okay. So so far we have not made any assumptions concerning the Xi's except that they are IID random variables. So the first assumption is the expectation exists. And of course, since these are IIDs, the expectation of each of the Xi will have the same expectation. So all these things equal to expectation of X1. So we will now find the expected discounted sum, the expectation of. So the importance of this is this can be considered as a kind of an estimate, that is the average amount estimate for the amount of money the company should have at time zero, so that it can meet all its obligations during the interval 0 to t. So t may be reasonably small, so that the premium income might not have stabilized, or it might not have become sufficient to handle in the exigencies. Yeah. So this IAD family, this sequence Xi is independent of NT and hence, of course, the WL. NT and WL are not independent. As a matter of fact, you can get hold of one if you know the other kind of situation. So we can verify now. That will be a long sequence of equalities. Okay. So expectation of S0t. So that is expectation of, by its definition, it is this. So as is now the thing, we just condition it with respect to NT equal to N. So it is this object, summation over N going from 1 to infinity, expectation of this I going from 1 to NT Xi times e to the power minus RWI, given NT equal to N multiplied with probability of NT equal to N. So if NT is equal to N, in this expression, you can replace the NT here by N. That's what we are doing here. Now, since this is a finite sum, there is no harm in bringing this summation outside this expectation. Now, we use our observation that these Xi's are independent of Wi as well as NT. So that can be taken out. So that would be expectation Xi times conditional expectation of this object given NT equal to N times Pn probability NT equal to N. But expectation of each Xi is expectation of X1. So that comes outside. So we take it out, and what remains is this. And once we do that, we take this summation I going from 1 to N again back into this expectation, because that's going to be advantageous for our next step. You can even guess what the reason is. Because in this object, to evaluate, we can use our theorem concerning the connection between the Poisson process and the order statistics. So this is equal to, we denote by dagger. Please note it down and also verify that I am not cheating you. Okay, we'll go to the next slide. So Now we are using that theorem. This is the theorem which connects the Poisson process with order statistics of uniformly distributed random variables. And also, we also use the notation as in that example 1 of that Poisson process 3. I think concerning this UIs. For each n, U1, U2, UN is a sequence of independent IAD uniform distributions, uniformly distributed over 0 to t, the interval 0 to little t. So all these things marked with a question mark here are something which you have to sort of convince yourselves. So since this kind of probability or event is same thing as this probability or this expectation. And this step follows because in this, the summation is I going from 1 to n, and here we are having a family of n independent uniformly distributed random variables. So all of them, all the order statistics of that is occurring here. So that the sum should be equal to same thing as summation I going from 1 to n e to the power minus r times ui without that braces or parentheses. So this whole expectation, these are IAD random variables. This expectation is same thing as e to the power, expectation of e to the power minus r times u1. And of course, there are n of them. So the n comes in here. So summation n going from 1 to infinity, n times p probability nt equal to n is same thing as summation n going from 0 to infinity, n times this. So this expression is expectation of nt. Expectation of nt is lambda t. So now this expectation you write in terms of the probability density function of the uniform distribution, and you have this. And again, this is a calculation you have to verify. So this expression we will denote by double dagger. Please note it down. Okay. So by the comparing double dagger and dagger, we get expectation of S0t is lambda times expectation x1 multiplied with 1 divided by r times the whole thing multiplied with 1 minus e to the power minus rt. So this, as I had mentioned earlier, an estimate of the initial capital to start the business. That is to meet the obligations during the finite time horizon 0 to t, when the premium income may not have become sufficient. can easily check that limit of the left side as R goes to 0 or decreases to 0, that is the rate decreases to 0, is precisely expectation of ST. That is the undiscounted total claim amount process, expectation of that. That is to be expected, of course. So we next consider the Kramer-Lundberg risk process and some aspects of what is generally called the ruin problem. If you want me to go back to any of the things concerning the discounted total claim, I will be happy to do that. Any of the slides. Okay, now we will go to the next slide. So we will introduce this Kramer-Lundberg risk process. As sort of alluded to here, we will now introduce the premium, etc. So we assume that the company charges a premium at a constant rate. And let's say C, little c is the premium rate. Of course, that has to be strictly positive. So the premium income for the company during the interval 0 to t is C times t. Okay. So define RT equal to X plus C times T minus S of T. And ST we know is summation I going from 1 to NT of Xi. So RT is equal to X plus CT minus summation I going from 1 to NT Xi. Of course, this X denotes the initial capital. So you have had some idea about how initial capital could possibly be chosen. Let's say by experience, one knows that the premium income takes about, let's say, 10 time units for it to become sufficient. Then T can be taken as 10 here, and this gives you roughly that estimate. So you have some way of getting this. Getting means in there it is one of the ways. So now note that this is the initial capital. C times T is the total premium income during 0 to T, and S of T is, this is the random element. This is the total claim amount the company will have to pay during 0 to T. So therefore, this will denote the capital with the company at time T. Yeah, that is called surplus. Of course, it can be positive or negative. If the surplus is negative, of course, the company is in the red at time T. So R of T is the surplus of the company at time T. That's a term used in this context. So sometimes this is also called RT Kramer-Lundberg risk process, or this is the amount of risk. Amount is at risk at time T, or surplus. So the process R is called the Kramer-Lundberg. But of course, this is in honor of the Swedish actuary Lundberg, who initiated this kind of a model to study non-life insurance kind of models in, I think, 1903. And Kramer, later on, the famous probabilist statistician Kramer, Harold Kramer, whose name you would have heard of, for example, Kramer-Levy continuity theorem and things like that. So he sort of amplified it and made many things quite rigorous in the 1920s and 1930s. Both are from Sweden. So as you may be knowing, the Scandinavian countries are generally considered welfare states. So insurance, etc., are given quite to the prominence. Of course, if there is a very major disaster or something, the government has to step in. Individual private companies, they may not be able to do, I mean, they may be able to do only up to, then big catastrophe and things like a large scale flooding and so on, the governments step in to take care of the marooned or affected people. So from our point of view, interesting or important concept involved is the so-called ruin. So we mentioned that, this RT can be positive or negative. Of course, if it is negative, that means RT is less than 0. It's in the red. So let us call this event, this RT becoming negative for some T greater than or equal to 0. So let us say this event we call it ruin. Ruin doesn't mean that the thing can go out of business. It could even be just a temporary setback. And again, things can recover and the surplus can turn out to be positive later on. Maybe initial capital was not enough, or soon after, let us say, the thing started, there were unexpected, after all, these things are random, these are subject to randomness, no? So something happened and temporary setback, and it can recover and so. Anyway, for the sake of defining it very precisely, let us call it, let us have. So this is union over all T positive, non-negative, such that RT is less than 0. That's clear. We are saying define the event. So that is this object. Well, of course, since we are, the next thing also says ruin probability, etc. We should be able to talk about probability of this guy. For that, this object has to be a genuine member of that sigma algebra, that omega AP, basic probability space, this has to be a member of that. But here you notice that this involves union over uncountable sets. So each of this is an event because RT will be a random variable each for each T. That is no problem because from the definition itself, you can see that for a fixed omega as a function of T, RT is right continuous. So consequently, it is enough to consider this event is same thing as, let's say, union over T varying over rationals or the dyadic rationals over the positive axis. So this ruin is a genuine event. It is this object which we have defined here is an element of that sigma algebra A in omega, capital omega AP. So it makes sense to talk about probability of this event. So those of you who are familiar with the measure theoretic niceties, you can sort of easily see this. Others, those who are not conversant with the measure theory and things like that, assume that it makes sense to talk about probability of such objects. Right continuity of this for each fixed omega is easy to see. Of course, this part is continuous. And here again, it is continuous except for the discontinuities for each fixed omega at the WIs. We have seen that earlier. NT is right continuous and the same property carries over to ST. Okay, note it down if you want. So one defines the ruin time, let us say tau 0 is infimum t greater than or equal to 0 or t strictly less than 0. Here, note that we cannot replace this by such a minimum because this is over a continuum. Now time varies over a continuum. So this way of writing tau 0 equal to inf t greater than 0 such that RT less than 0 means at any omega, tau 0 omega is infimum of t greater than or equal to 0 such that RT omega is less than 0 if this set, that is the set of all t greater than or equal to 0 where RT omega is less than 0, that set for a fixed omega of course, is non-empty. That is, if there exists actually a t greater than or equal to 0 such that RT omega is strictly less than 0. Otherwise, this is equated to plus infinity. That means, what does it mean? If for a particular omega, tau 0 omega is plus infinity means it never goes below 0. This never happens. Of course, Boolean probability is probability that tau is strictly less than infinity given R0 equal to x. I mean, this is expressed as a function of the initial capital. If the initial capital is x, the probability that the probability of ruin is, I mean, this thing, tau 0 is less than That is the probability of ruin if the initial capital is X. So which we also denoted by P sub X tau 0 less than infinity. Please note it down if you want. Yeah, so this is the psi of X is probability of ruin in finite time with initial capital X. So tau 0 less than infinity means ruin is happening in finite time, at some finite time. All right. So the event tau 0 equal to infinity, that is, this thing can possibly happen with positive probability. If that kind of a thing happens, that would be desirable from the point of view of the company. That is, ruin never happens. So this is a, you can say, a desirable possibility. So this would mean the probability of non-ruin is strictly positive. So we are going to make one important observation. So for notational sake, let us denote by W0 equal to 0. So that many things in what follows can be written in a unified style. And WIs, let's say, which are in increasing order, be the successive claim arrival times. Okay. All right. Now we will go back. Yeah. So ST is equal to this. You just look at ST. I don't want to go back to the that place where we have defined ST, but this is good enough for all. See, from 0 up to time W1, this NT would be 0. So this is just 0, it doesn't change. And between W1 and W2, it will be just I going from 1 to 1. So it is just X1. It doesn't change up to time W2 and so on. So between any two WIs, let us say closed at the lower end and open at the other end, higher end, that is W1 closed at W1 and W2 open. This ST remains a constant. So it doesn't change. And let us say between W1 and W2, let us say closed at W1 and open at W2, X plus CT is increasing. Since C is strictly positive, you can even say strictly increasing. So that is going to be our observation. Yeah. So note that the compound Poisson process ST does not change on Wn to Wn plus 1, closed at the lower end, open at the open. Yeah, since a claim arrives here at this time there could be a jump. Hence, as we have seen, this R is strictly increasing in that interval, Wn to Wn plus 1. What is the meaning of ruin? R going below 0. That means if it is strictly increasing, if there is no ruin has happened at n plus n, it cannot happen before arrival time n plus 1. So ruin can occur only at a claim arrival time W. And this is the last slide for the day. So this is an important observation, and because of this, our analysis of this situation, I mean, it becomes tractable. So we are going to use this observation to our advantage. So if you want me to go back to any of the previous slides, I can do it. I'll be happy to do it. Okay, otherwise we'll stop sharing today and continue on Wednesday. All right. So if no questions or comments, I can end the session today. Okay, thank you all, and we will see again on Wednesday. Take care.